Hello everyone and welcome to a video on critical path analysis. This is the second last section in the Year 12 General Maths course. It's also one of the more challenging topics. And my aim in this video is to get you started on some of the theory and work through a few examples. The terms that are highlighted in yellow will appear later in this video, and I'll explain all of them. But for now, let's launch in with a review of what we did in the last lesson. So last time we went between two different representations of projects. The first was a table of activities and a relationship between those activities, which we called immediate predecessors. So these are the activities which must be completed before the activity can begin. And in order to make sense of this sort of table, we found it helpful to draw a graph. The start of a project on the left, and conventionally the end of a project on the right. And it wasn't super easy to do this, but with some experience you'll be able to do something like this. So I'm seeing that activities A and B here have no predecessors, and so they must come off the start of the project, and we're going to represent each activity with an edge. You'll also notice that I've drawn arrows. That's important because that's showing my progression from the start towards the end of the project. Next we have activity C, and A must be complete before activity C can begin. And similarly, activity D requires B to be complete before it can start. Now, you'll notice that activity D is not a predecessor to any other activity. So that means it's going to go straight to the end like this. And activity E, which comes off C, will go to the end as well. So that's what we did last week. We went from a table to a graph, and a graph to a table. Today what we're going to do is we're going to add numbers to this graph. Those numbers are going to represent the amount of time it takes to complete an activity, and our goal is to be able to work out how long it's going to take to complete the project. And we're also going to look more deeply at which activities are sort of central to that completion time. So we're going to find that some activities can be delayed and other activities cannot be delayed without holding up the entire project. And so if you're a project manager, someone running a company, you care about these things because these represent the pressure points or the bottleneck of your projects. So in our activity table, we're going to add a new column. Usually we call it the duration. Just think of duration as length or amount of time. And all I'm going to do is I'm going to copy this graph and paste it. So I've already stated the goals. I won't repeat that again. Paste it over here. And before we continue, I want to introduce two new terms. The first term is the earliest starting time, and the second term is the latest starting time. It's pretty self-explanatory. The earliest starting time is the earliest time that an activity can begin. And the latest starting time is the latest time that an activity can begin without delaying the whole project. If you're seeing this for the first time, it might surprise you that these two times would be different. I think this will become most clear when we work through an example. So what I'm going to do from this point onwards is I'm going to do a calculation that you're going to need to do on your own. So what we're going to do is I'm going to draw two boxes and I'm going to write a letter next to them. So the convention that we're going to use in this class is the activity is named on the left. The earliest starting time is in the box on the left, and the latest starting time is going to be in the box on the right. So remember that. Whenever I give you a graph with the duration of the activities, expect to draw these boxes for every single activity in the graph. And we're going to fill the boxes in, and I'm going to show you how to work this out now. So this is the same graph that we had previously, just with the added information of the duration in this third column. So our goal now is to work out what is the minimum time needed to complete this whole project. So that means all of the activities A, B, C, D, and E must be finished. So step number one, we need to draw a box for every single activity. So I'm going to go ahead and do that now. And I want you to think of these boxes as coinciding with each vertex in the graph. So we'll have a box for activity C, a box for activity D, a box for activity E, and you're going to need a box for the end as well, because that's going to represent how much time it takes to do the entire project. Now, we're going to put the EST on the left and the LST on the right, and we've named the activity on the left. So, let's work through this example. First of all, let's look at activity A. The earliest that this activity can start is at time 0, because it's at the beginning of the project. Same thing with activity B. Now, what I need to do before doing anything else is include the information on the duration of the activity on the graph. So I'm going to go ahead and do that now. Normally, in the exam, the graph is given to you with the numbers. They might not give you the table, but it will look something like this. So you'll notice I've put the name of the activity on the left, then I've got a comma, and on the right of the comma, I've got the duration of the activity, and this is along every edge in the graph. Now that the information is in the graph, I no longer need to look at the table, and I can just focus on filling in these boxes for the EST and the LST. So, activity A takes us 3 weeks. So that means activity C, which has activity A as an immediate predecessor, cannot start until A is complete. If A can't start until time 0, that means C cannot start until time 3. Activity C goes for 2 weeks. And we can't start E until C is finished. So C can't start until time 3 plus 2, which gives us 5. Now, let's go along the bottom now. Activity D cannot start until B is finished, and B takes 4 weeks. So the earliest starting time for activity D is 4 weeks after the project has started. And now we're at a crossroads, because now we're looking at the end, and there are two activities converging upon the end point. We need to decide whether the earliest starting time of the end of the project is going to be time 12 or time 9. So let's think about this logically. Activity D cannot finish until at least time 9. Activity E cannot finish until at least time 12. The project is not finished until both activity D and E are finished, which means we must take 12 to be the earliest finish time of the whole project, because we're limited by activity E, which we have to wait longer to finish. We have just completed step 1, the green writing. This is called the forward scan. The forward scan is where you find the earliest starting time. So you'll notice I worked from left to right in the graph. Now we're going to work the other way. I'm going to do this in a different color as well. So now let's look at the latest starting time. We're going to assume that we want to finish the project as quickly as possible. So we still want the latest starting time of the end to be 12. And this is where things are going to get interesting, because now we're going to see that some activities can be delayed and some other activities cannot be delayed. For example, let's look at activity E. We know that activity E takes 7 weeks. We want the whole project to finish at the latest by 12 weeks. And that means there's really no leeway. Activity E, latest starting time is also 5. Let's look at activity D now. We know that activity D takes 5 weeks. And we know we want to be finished by the 12th week. If we do 12 minus 5, we get 7. So what we're saying is, activity D can start as late as week 7. And if we do that and still allow 5 weeks for activity D to take place, we will still finish the whole project without holding up the finish. So activity D can start as early as week 4, and I can wait until week 7 without holding up the rest of the project, because I'm limited by what's happening with activity E. Let's go backwards again. Let's look at activity B. We know that activity B can start as late as week 7. We also know that activity B takes 4 weeks. So that means if I do 7 minus 4, that gives me 3. So what I'm saying is activity B can start as late as the 3rd week, and still we can finish the whole project in 12 weeks. Now, if I do this, the top, 5 minus 2 gives me 3. 3 minus 3 gives me 0. What you're seeing here is that the top activities, A, C, and E, they're the ones kind of limiting the whole project. 3 plus 2 plus 7 gives me 12. 4 plus 5 gives me only 9. So the longest path from the start to the end is this one. These are the activities which cannot be delayed without holding up the end of the project, 12 weeks. On the other hand, there's another path in the project, B and D, which takes less time. The activities on this path can be delayed without holding up the entire project. You'll also notice that the activities on the yellow path, A, C, and E, they all have an interesting property. All the activities have the same LST and the same EST. So if I fill in this table now, you'll see the following. LST and EST are the same. In a moment, we're going to give this a name. We're going to call this the critical path. And the critical path has all of the activities which have a float time of 0, but I think I'm getting ahead of myself, so I won't discuss that just yet. But for now, we have worked out the earliest starting time and the latest starting time of all of the activities in this graph. So let me copy this because we're going to reuse this result again. And now let me explain just a few more terms. So the float time is the first thing I want to explain to you. This is the difference between the latest starting time and the earliest starting time. The float time tells you how much time we can delay an activity without increasing the length of the whole project. The critical path has all of the activities which cannot be delayed. Any activity which is on the critical path will have the property LST equals EST. And a consequence of this is that the float time will be 0. When you're analyzing a project such as this one, your goal is to locate the critical path, because that's going to tell you which activities you can't delay, and it's kind of like the longest path from the start to the end. So if you found the critical path, then you can simply add up the numbers on that path to get the duration of the whole project. And when we do something called crashing in the very last lesson, we're going to want to shorten a project by reducing the length of an activity. And the only way we're going to make any savings, that is, to make a project happen quicker, we're going to have to shorten activities on the critical path. But that's for next time. One final remark before we do another example is that it's possible to have more than one critical path. When you start working through exam questions, you'll see this come up all the time. They like to ask questions to really test your understanding of what's going on here. So, please remember, EST means the earliest starting time. LST means the latest starting time. The float time is the difference between the two, and the critical path has all of the activities where the float time is 0. That is, the activities can't be delayed. These are all terms that you need to know, And you should have these written down in your bound reference. But don't worry about memorizing them, because once you've done lots and lots of questions, you'll just know this. Okay, so let's return to the graph that we were looking at just now. So I'll copy this over. Oh dear. Okay, so remember, float time was LST minus EST. So that means the float times are as follows. And any activity with a float time of 0 is going to be on the critical path. So that means activities A, C, and E. If I go back to the graph that we drew before and copy this over, you'll see that this matches the yellow highlighting that we did just now. Sometimes you'll be asked for the critical path, and I'll just add step 2, which we did in orange, was to find the latest starting time. And notice that we started from this end and we worked backwards. So for the forward scan, you go from left to right. To do the backward scan, you go from right to left. Sometimes you'll be asked for the critical path. And in this case, the critical path is A, C, E. You might also be asked for the minimum completion time of the project. In this case, the minimum completion time of the project is found by looking at this last box, which you drew for the end. So the minimum completion time in this case is 12 weeks. Okay. Let's do one more example. Step 1. Draw a box for every activity. And draw it bearing in mind that each vertex represents a point where a new activity starts. So I want you to see these boxes as associated with these vertices on the graph. Now, you'll notice at this vertex at the start here, there are actually 2 activities. Please make sure you draw boxes for every activity. If you do this, you will avoid lots of errors. Because a lot of people will forget about this box and they'll assume that A and B have the same earliest starting time and latest starting time, which is not true. You need to see these activities as separate, and there could be a delay in one activity but not the other. So we'll continue. Step 1, draw a box for every activity. The reason why I am writing the letter as well is just to make it really clear and unambiguous. And remember, this last box here is for the finish. Okay, step 1, or step 0, draw the boxes. Step 2, do the forward scan. That is to find the earliest starting time. Activities A and B have no predecessors, so the earliest starting time is 0. Activity D cannot start until activity B is finished. Activity B has a duration of 6, let's say, hours. So that means activity D has an earliest starting time of 6. Activity C has an earliest starting time that's dependent on having both A and B finished. Because remember, this dummy activity here is saying that activity B is an immediate predecessor to activity C. So now we have to choose between 6 or 9 as the earliest starting time for activity C. We have to go with the higher one because we can't wait 6 hours. 6 hours isn't going to be enough because activity A won't be finished. So the earliest starting time for activity C is 9 hours. Let's look at activity E now. Activity E cannot start until activity D has finished. 6 plus 4 gives us 10. And let's assume that activity G is going towards the finish as well. Okay, let's look at activity F now. 9 plus 7 gives us 16. 10 plus 5 gives us 15. We have to choose the later one, because if we wait for 15 hours, activity C won't be finished. Activity C will still be in progress. So that's why activity F has an earliest starting time of 16. Activity G is here. It has the same earliest starting time as activity E. That's also 10. Now for the finish. 10 plus 2 is 12. That's activity G. 16 plus 3 is 19. We have to choose the larger one. So in this case, we are noting that activity F will be the last one to finish. 16 plus 3 gives us 19. That's step 2. Step 3. Do the backward scan to find the latest starting time. All right. When you do the backward scan, the numbers in the very last box for the end of the project are always going to be the same, because your goal is still to finish the project as quickly as possible with no delays. So you're going to treat those times as the same, but now when we work backwards, we're going to find that some activities will be critical activities in the sense that they can't be delayed, and some activities can be delayed. For example, activity G requires 2 hours. But activity G doesn't have to start until the 10th hour. If I do 19 minus 2, I get 17. Activity G takes 2 hours. So even though activity G can't start until the 10th hour, we can actually wait an additional 7 hours before getting started. Now, activity F is next. Let's look here. 19 minus 3 gives us 16. 16 minus 7 gives us 9. 9 minus 9 gives us 0. So, you'll notice I've listed some activities here where the earliest starting time and the latest starting time are the same. They have a float time of 0, which means they are on the critical path. Now, let's check whether there is another critical path on this graph. Let's look at activity E. 16 minus 5 gives us 11. So that means activity E can be delayed by up to 1 hour. Let's work backwards again. 11 minus 4 gives us 7. So although activity D has an earliest starting time of 6, we can actually wait an extra hour until hour number 7 without delaying the whole project. And if we go backwards again, 7 minus 6 gives us 1. I have not found any other situation in this graph where the earliest starting time and the latest starting time is the same. So that means there is only one critical path, and that is ACF. And the minimum completion time is 19 hours. Okay. Why don't we do one more? I just want to illustrate a situation where there might be two critical paths. Okay. In this graph, I want you to notice that this path has a length of 10. This path also has a length of 10. But this path only has a length of 9. If we do the analysis again, and I'll try to make this quick. We've got to draw the boxes for every activity. So let's start with the forward scan. Activities A, C, and E have no immediate predecessors. So that means their earliest starting time is 0. Activity B cannot start until activity A has finished. So the earliest starting time of activity B is 7. Similarly, the earliest starting time of F is 2, and the earliest starting time of D is 4. 7 plus 3 gives me 10. 4 plus 5 gives me 9. 2 plus 8 gives me 10. I must pick the biggest number. So that means the earliest finish is 10. Let's work backwards now. 10 minus 8 is 2. 2 minus 2 is 0. 10 minus 5 is 5. 5 minus 4 is 1. 10 minus 3 is 7. 7 minus 7 is 0. So you'll notice activities A and B, activities E and F are on critical paths. This graph has 2 critical paths. The first one is A, B, and E to F. the minimum completion time is 10, let's just say hours. You'll be told what the time is in the question. Okay, so let's do a very quick recap. We started off at the very beginning by reviewing the fact that we could move from a table to a graph. Each edge on the graph represented an activity in a project. When we have one edge before another edge, we're saying that the first edge, in this case the yellow edge, is a predecessor to the next activity, here represented by the blue edge. The next thing we did was we introduced numbers, a duration associated with each activity. And our goal was to find the minimum time required to complete the entire project, which meant all of the activities needed to be done. And what we found was that some could be delayed and some couldn't be delayed. We then introduced some terminology. We introduced the notion of the earliest starting time and the latest starting time. So some activities can't start until you've waited some time for the other activities to finish. But we've also found that some activities can start after their earliest starting time because there are other activities somewhere else in the graph that take longer, and so we can wait. We then worked through a few examples where we broke up the process into a few steps. The first step was to write the boxes. You must make sure that you write the box for every activity. If you do that, you won't run into any problems. Next, you needed to do the forward scan, which started on the left and finished on the right. Then you needed to do what was called the backward scan. This time you started on the right and finished on the left. Once you've done that, you'll find that some activities have instances where the earliest starting time and the latest starting time are the same. When this happens, those activities are on the critical path. And activities on the critical path cannot be delayed. If you delay any activity on the critical path, you will delay the entire project. Which means, and this is a preview of the next lesson, if we want to shorten a project, we have to start by shortening activities on the critical path. We won't get any savings if we try to shorten activities which aren't on the critical path. So, when you're analyzing a graph, you should always draw the boxes. You should work out what the critical path is, and make sure that your float times of 0 match what you expect. So in this case, the minimum completion time was 12. So that means if you found a number 12 with your analysis, if you add up all the weights or all the numbers on the critical path, you should get 12. So 3 plus 2 plus 7, that gives us 12. As always, I will upload these notes to Teams, but I hope that you found this video helpful, and remember to ask me questions in class if you have any. See you next time.